Okay, so we're going to run through the, not necessarily the build, but the full Excel taking readings from MultiSim. So MultiSim circuit's been built. Previously, you got two 10Ks, R1 and R2. So just to keep your distinction between charging and discharging, that means your tau is going to be different, your time constant. Whether we're in charging position, we're going to have R1 and R2 in series with each other, gives you a 20K for the charging value. And then for discharging, we're obviously going to have our circuit's going to be a short circuit down through with just R2 and C1 involved. So your discharge resistor value is going to be only 10K compared to the 20. So we're going to have a difference. Voltage supply is 120. What we're interested in getting connected up here is our oscilloscope. So place it in your oscilloscope, pick it off from the right hand side. We're only interested in channel A for this particular one, so we draw in our channel A, the negative side, place it anywhere along basically your ground connection would have done, and then your A connection here, we'll just put a few clicks in, tidy it up, but we're just going to go in between our R2 and our C1. You can change color if you so wish, segment color, change it to black for instance, and then when you open up this and run it, we'll just very quickly run the test, and I hit play on this one and go to reverse. We go to see, and then if I then click on the screen, operate the switch here, and we operate with C, it obviously shoots up. We're out of range effectively there, so what we want to do is affect our channel A, is the only one we're actually interested in. We want to adjust our scales until the line basically becomes visible. So we have 50 volts per division, so each of the granulated or dashed lines there is going to be 50 volts, so 50, 100, and then obviously 150 at the top. The black line you're seeing there is effectively your 120 volts for your supply being shown. So to be able to observe that from the very start, if I just switch it back to the discharge position and just turn it off, back on again, and then when I operate the keystroke, you see it goes in. The only bit we need to do now is adjust our time base, which is our effectively our x-axis, which is now going to be 50 millivolts per division. Let it level out for a period of time. You can press pause or stop, doesn't really matter. And then what we're going to do is to take readings, we want to move our cursor here, and we want to put it to the point at which the graph effectively began to rise up. The easiest way to do that is go to right click on your cursor, right click and do the Y value to the right, and you're just looking to place in a very low value, for instance, hope had zeros or 1, and then your cursor will jump to effectively the first instance at which your graph began to rise up at that stage. So what we have is our channel A shown at 0 volts, which is effectively ready to just begin rising. Obviously it's shortened it down to 3 decimal places. We selected one with a lot more decimal places than that for our actual value. But our time, that's the other bit we're interested in, is 35.923 milliseconds. That's effectively our zero time, we call it. So that's the point at which our graph begins to rise up. So what we're looking to do then is go on to our Excel. The table that you have in your assessment paper looks something like this. So you've got time in milliseconds, VC, VR, and then your current, that's your discharging, and then our charging circuit. Now, just for the handliness of what I have, you're going to have on your table, for instance, 0, 5, 10, 15, and so on filled in here. I need to figure out what my time base is going to be. The structure of it is going to be for tau, so I need to find out what my tau is. Now the graph is going to be the same for everyone, so it's going to be 0, half, 1, 1.5, 2, 3, 4, 5, and 6 tau. From that, I can calculate for my particular example I'm doing right now what my time will be. Now remember, for yours, your time is given to you, so this wee stage here, you don't really need to do. That's just for me, for my example. So I need to effectively calculate my tau. So I'm going to need a couple of things. I need to actually have my R value. For charging circuit, it was 20,000. And my C value is the capacitance value. It's a 1 microfarad. So if I type that in, it's 0.51. It's going to be there. Just displays it as 1 times 10 to the negative 6 effectively there. And my tau is a very simple calculation. So equals to the 20,000 multiplied by the capacitor value, and it comes out as 0.02. Now, by default, that comes out as seconds. Now, as you notice here, my time here for this particular column wants to be in milliseconds, so pretty easy conversion. So it equals the time in seconds multiplied by 1,000 to convert it into milliseconds, right? And that's the value I can now use. That's my tau in milliseconds. That's one time constant. So that's up in there. So that value there is effectively my tau. All these other ones here, I can now very easily basically calculate. I can go equals 2. So that's this one here is going to be half a tau. Now you can do it obviously in your head. It's going to be 10 milliseconds. But it's obviously easier to fill in the rest using a formula. So it's going to be equals to that. And then you want to lock that in. So you press F4 to lock it in. And you multiply it by the tau value beside it, which again gives you your 10. And I can drag that up, which is going to be 0. And because I'm using both sides of it, I just need to re-enter here. So equals the original, lock it in, multiplied by the tau value beside it. And then I can drag that down for the rest. Right, nice and easy. So what I've entered in, I'll put in yellow, just so it's easy to see. And then any other bits is going to be calculated effectively by the software. Now that I have that, what I really want to find out here, which is an easy one to add in, is an actual time in milliseconds for this. Now, I'm going to enter the first one, but the rest I just want to calculate. So this is effectively where I move my cursor on MultiSim. The very first one is that value that I had there, which is 35.923. So I'll put that in, 35.923. And then every other one of these is effectively that time added on to whatever my time increment is from that column. So I can calculate all these just to have them pre-readied. So it's just equals to, and it's the one above, lock it in because I'm using it every single time, and I'm adding on whatever the time base is there, which gives me that one, and then I just drag that down. So that's where I need to move my cursor to take my readings for VC. All right. So the VC is going to be the measured one. I'm going to enter all those values, and then finally I'm going to use what will be the yellow column here to calculate the final two columns. So let's actually take some readings here. The first one is 0.000, so it's 3 decimal places. Now, here I already have it formatted. Yours would probably be by default 0, I'm going to guess. But you can go right click on that column, format cells, and just make sure you're on number. Change your decimal places here to be 3, and then obviously hit OK. Just means what you enter is going to be the same as what you read from MultiSim, just to keep it the same. So all I'm going to do here is I'll go split screen, and I will select that, and I'm looking to basically move my cursor here so that I can take my readings a wee bit easier. So I'm now looking to move my time is my x-axis. So I will right click on the red cursor. I want to set my x value. So automatically it comes up with where it's currently at, which is at 35.923. You can, half the 6 of one, half a dozen of the other. You can literally click on it and just change the value, say 45, and press enter and you see it move, or you can obviously right click, change x value, just delete it out and re-type in your entire number, your choice. When you type in your entire number, remember to put in your M for milli. Otherwise it just jumps to the end. It tries to go to like 45 seconds instead of milliseconds for that particular bit. And then I'm just keying in my values here. So that is 47.198. And then just repeat the process. So it takes a few seconds to do this, but that is 75.842. And then I need to go to 65. Which will be 93.215, then to 75 milliseconds. And I get 103.753. Just going to move my blue cursor out of the way so it's not confusing numbers. X value, we're now up to 95 this time, which is 114.021. I did not type that right. 115.923 milli. prime example there of why it's great to have your time written down if you make a mistake like that. That is 117.798, and then 135. Gives me 119.187, and finally, last one, we get into 155, which gives me a value of 119.698. Okay, so we just make this the large version again. So that's now all my measured values for VC. That's the voltage across the capacitor. For VR in a charging circuit, it's very simply your supply voltage, which we'll just list over here, which is 120 volts, because I want to be able to use this in calculation. It's just going to be that there minus whatever's across each of these is what's left over. Because in a closed loop circuit, all voltages must equal 0. So your supply is going to be effectively your plus value. That's what's used up by the VC. The other part of the calculation is what's left, which is your VR. This is a very simple calculation. Your VR is equal to your VS. Lock it in because you're going to be using it every single time using your F4 minus the column beside it. And then I very simply drag that down for each of those. And if I could drag it down, we'll move better. There we are. And then the calculation for the current very simply is your I is equal to your V over R. And slightly more specifically, it's actually VR over R. So we'll show you the first example if you just do that directly on what it comes out as. So we're going to say so the I here is going to be your VR, so it's this one, divided by your R. Your R value is 20,000. Now it's always going to be the same one, so we just lock that in. Now if I press enter at that point, I end up with 0.006. Now V over R just gives me amps. Now the column here says I want it in milliamps. So the easiest way to do that is just go up to your calculation again and just edit it up in your top area and put the initial bit in brackets and then multiply by 1,000, converts that into milliamps for you. And again, drag that down so you now have your milliamps. Now, I produced a couple of graphs. I'm not going to look up which ones were produced. I'm just going to pick two at random. So there's current and times. That's your X and Y axis. So your X axis is time, your Y axis is your current in amps or milliamps in this case. So highlight those two columns, go to insert, recommended charts, and then should be by default, as long as you've selected the right columns and so on, it should be scatter graphs is the one suggested to it. That's what we're looking for. Just place it in. What you need to add is your axis titles, and then you want to add in and change those to, for instance, for this one here, for x-axis it's going to be time, and then make sure you put in your units as well, which is going to be milliseconds as an example. Time, and then y-axis for this one is going to be your current, which is going to be in milliamps. And then change your chart title again, something like graph to show the current in a charging circuit, or something to that effect. Make up your own title, obviously. But you're asked for two charts, so I'll just quickly show you another one. I'll do VR against time this instance, and go insert, recommended charts again, scatter, and again place it somewhere on your page. And just remember then, add in your axis titles and obviously change those two values as well for that. So that's your two axis titles, and obviously remember to change your chart title too. So that's charging. So let's go and look at your discharging as well. So again, we'll set up, we'll just take that as a header this time and copy it across. For this is our discharging circuit. Again, tau 0, half, 1, 1.5, 2, 3, 4, 5, 6. Again, our actual time is what we're actually going to put in. We're going to be typing that in. And again, we'll be taking readings for VC. Again, as previously, we'll do calculations for the previous two columns, but this one's going to be for a discharging circuit. So your R value is changing, C value won't. Therefore, your tau will change. So discharging is going to be 10,000. 5 and 1. Therefore, your tau equals to, similar to what it was, obviously, but that multiplied by your C value. Once again, that comes out in seconds. So just to convert that, we do equals to your tau value multiplied by 1000, which converts it into milliseconds. So I now have a tau value of 1 here, is our 10 milliseconds. Same process as before, we fill in the rest of these, so it's going to be equals to the original multiplied by the tau value, which is 5. That's going to be 0 anyway, but equals to original, lock it in, multiplied by the one beside it, and you can drag down. So we now have our increment values. So these are the values we're going to increase our actual time by here. So let's actually find out what our actual time is for a discharge circuit. Hop over to MultiSim. And we're going to go to discharge. The easiest way of doing this is to stop your circuit, place your switch to make sure it's in the charge position. That means when you first turn it on, if we just display it here, it starts off at the charge position. Click on your circuit, press your space bar to operate your switch, give it a little bit of time to run out, and then pause your circuit. And we're now able to take our readings, space it out a little bit. This one here, you maybe notice that your A channel, instead of being 120, which is what you might expect because that's obviously the supply voltage, it actually is slightly below. It's just the way the software does that. So to do this particular bit, what you want to do is set your Y value to the right this time and just drop your end digit. So instead of 6, put it to like 5, and it rounds off to the first time at which it begins to drop off. Not just as easy as the charging one. But there's now your charge, or your discharging rather, time to start with, which is going to be 81.043. So again, repeat the process here. Just flip them into the right areas, and we have 81.043. Now all these increased times are just going to be equals to your original, add on whatever your increment value is, and then drag down. Right, that's where we need to move the x-axis cursor to take our readings. So the first one is going to come in at, place in 119.996. Basically, obviously if you do 2 decimal places, it will be 120. Obviously the software shows it a bit more accurate than that. So let's increase and take all our readings. So change your x value, which is going to be 86 for this particular instance, and take a reading which comes out as 72.816. And again, just a wee bit of time obviously needs to be used to get this done. Go to 91, which is going to 44.165, and again just progressing through. 96 comes out as 26.788 volts. Rinse and repeat. 101 comes out as 16.247. And we're now going to 111.043 milli, which is 5.977, 121, 2.199, and the last two comes out as 131. Here's your first sort of anomaly. The reading that your oscilloscope gives you is now in millivolts. Obviously my column is said that they're all meant to be in volts. So I need to obviously convert that. So 808.914 milli is just 0.808 volts. And then the final one's going to be the same. That'll be 141, which comes out as 297.583. So that's 0.297 for that particular one. So we'll finish off the rest of this over here. Your VR for discharge. Keep in mind your circuit here. Get rid of that. When it's in the discharge position, your circuit is only two elements. You've got R2 and C1. So keeping in mind Kirchhoff's voltage law about in a closed loop circuit, all voltages must equal 0. If that there's a plus number of whatever value, to make your answer equal 0 for a two-element circuit, that must be the negative version of whatever that value is for the voltage drop across it. So very simply, your VR in this instance is just equals to the VC value multiplied by minus 1. And that is the same the entire way down. Right? So the voltage across the resistor is effectively the negative version of whatever's across that. Because there only is two elements in the whole circuit, which is VR and VC. Therefore, those must equal 0. So those two added together obviously equal 0. The current, again, same format as what was done for the charging side of things. So it's rather I is equal to V VR over R. And obviously, if VR is negative, the answer is going to come out as negative. So again, equals to the VR, which is there, divided by your R value, which is down there. Lock that in using F4. And what we'll do straight away this time is put our brackets in to convert it into, if I could not mess it up, F5 multiplied by 1000, and we come out, now the answer is already in milliamps. Drag that down, and again, you can produce two charts. There's current, time, so that's your y-axis, x-axis, insert, recommended charts, scatter graph comes up by default, place it into it. Just remember to add in your axis titles, obviously change them. For instance, that would be time in milliseconds, like so, and this one would be current in milliamps. And if you had to produce another one, we'll just do VC this time, VC against time, so X and Y axes, recommended charts, again, pick scatter, place it in, and obviously add in your axis titles, which I'm not bothered changing this time. But that's how you produce your graphs. So that's for charging and discharging. So charging wise, you're entering, taking your readings, calculating your VR and your milliamps, you're discharging. Those two are basically just the negative versions of each other, and then you should end up with negatives in terms of your current, obviously just indicating that the current's going the opposite direction to what you originally measured it. It's not actually negative current, keep that in mind. But that is the full run through with MultiSim and all the readings involved for tasks 1 and 2.